Welcome. In this lesson, I will be giving an overview of high-performance computing. I'll be doing this by giving first just an overview of what high-performance computing is and kind of some of the technologies behind it. I'll give some common terminology that's shared across multiple HPC centers, and then I'll dive in on some of the concepts and kind of key points of what you'll need to know to really make use of the strengths of high-performance computing. So to start off with, what is high-performance computing? Some terms you may have heard would have been like supercomputers or clusters. And clusters is really the strong word, the closer definition. An HPC system is usually, at this point, multiple machines, multiple computers, desktops, servers, anything that can do computations, networked together with a fast network connection, usually something like InfiniBand, with a shared file system that can allow users to request and then get allocated resources on the compute. So the key thing here is that you're getting your speed up by being able to run your program, your script, your software on data sets all at the same time. Being able to do things in parallel, which is another term that you'll hear a lot when it comes to high-performance computing. Another important thing is the difference between high-performance computing and high-throughput computing. HPC clusters can typically do both. In a high-performance computing, you'll have a program that can make use of multiple servers, multiple cores, but you'll be able to kind of dictate the flow of that. So you can be able to maybe have portions that are done in serial, then they can branch off and do things in parallel, or it might have data that might rely on previous results, or you might have to do everything on a huge whole data set. High throughput computing is if you have a data set that you can kind of break up and run the same operations on each subset of data at the same time. So you're running a lot of tasks all at the same time that don't really need to communicate with each other. They just need to know what data they're working on and making sure that they're not working on the same data as another task. You'll hear embarrassingly parallel a lot in regards to like high throughput computing. So that just means that you can run the same thing on all your data set. So how do you speed up your programs? The initial idea that people typically think of is they'll be able to jump onto an HPC cluster on our supercomputer and their program will just run magically faster. I wish it were that easy, but unfortunately you need to make sure that your program has some degree of parallelization where it can do multiple operations at the same time. And then finally, unlike your traditional desktop, phone, laptop, you're on a shared resource. You're going to be sharing resources, both the computational resources in a lot of cases, and like your login resources with other researchers and other users. So you're going to have to keep that in mind when you're kind of logging in and doing stuff. And here's just kind of a basic diagram of what HPC is. So on your left over here is your workstation. This could be a workstation, a laptop, even a phone nowadays that you're using to communicate with some system that has access to like the job scheduler, which we'll talk about a little bit more in depth in a moment. So these can also be like a data transfer node if you just need to get data onto the system, and it could be some sort of service node. Maybe you only interact with a database, you update something in a database, and that kicks off a job. So it takes your request for resources, and the job scheduler here will take that request and put it in the queue. It'll try to schedule it, and then it goes to the compute nodes over here. Each of the shades or colors here represents kind of a different job. So as you can see, there's a giant pool of compute resources of just servers that these jobs can access and then run their program on. And then again, there's usually a shared storage that's shared across all the compute nodes. Most compute nodes nowadays don't even really have hard drives in them. It's changed a little bit with the rise of artificial intelligence, machine learning, but generally, you don't even have hard drives in them because you don't want to have any sort of state in between jobs because you never know if you're going to jump on the same node again. All right, let's talk about some HPC terminology, and I'll try to focus on terms that will be generally shared across multiple HPC centers. Many centers have their own specific terminology that they might use, but this is kind of what's typically common across multiple areas. And the first is a job, which is just kind of the allocated or requested resources you've asked for on an HPC cluster. Usually access this through a job request. Usually this is like a batch script or some command line arguments you put on in the Linux shell, asking for resources. Hey, I need this many CPUs, I need this many nodes, I need this much memory, and these many GPUs. This request then goes to the job scheduler, which is a program that manages all these requests based on what's currently running, what people have already asked for, kind of time limits. There's a whole lot of factors that can go into scheduling when this job will actually run. And that's what the job scheduler does. There's a queue, which is all the jobs that are submitted to an HPC cluster. These can be jobs that are currently running. It could be jobs that are waiting to run. And it's just kind of the giant list of what's running. And usually they give you some indication of why a job might be waiting, and you can kind of get a whole kind of state of what the cluster is in usage. The node is a unit of an HPC cluster. This is typically a single machine or a single server. So it has all the memory, cores, GPUs, if it has it, CPUs. That's what a node is. And then there are cores, which is a single CPU or CPU core that's in one of these nodes. So typically you have to request one or the other or both. And you kind of base your program based on if you have access to multiple nodes, if it can talk across the network, or if you're confined to a single node, you might be able to request a certain amount of cores on a single node. On a smartphone, for example, you have typically like 6 cores maybe. And so if your program can make use of multiple cores, you'll see some speed up because most HPC compute nodes have more cores than is typically found on a desktop, phone, laptop. So then you have specific types of nodes. One is a compute node. This is the nodes where the jobs are actually run. You won't be able to log in directly to these. Usually you have to put in your job request and then you'll get access to it. And generally you don't even really ever log into one of these directly, but there are some exceptions. Login node is the entry point, so where you actually go to like copy files, submit your jobs, maybe even download and compile code. Usually you access this through Secure Shell or SSH, but nowadays there are a lot of web applications such as Open On Demand that will also give you kind of access to an HPC cluster. And then you have your different directories. First, your home directory. This is common across many Linux distributions, and Linux is the operating system of choice for most HPC clusters. This is where your like kind of longer term files, maybe even some programs and code will be. Also your configuration for your shell and any other programs that look in your home directory. Scratch is usually a high performant, fast parallel file system that's not backed up. So it's used for kind of temporary files, such as input that can be re-downloaded and output from your program before you copy it over to longer term storage. And then some centers have what's called an archive directory. This is more your long-term storage where it's usually backed up, and sometimes it can be tape backed. So it has a magnetic tape that stores the data in a giant library, just because magnetic tape is one of the cheaper storage options per byte. So now we're going to talk about some standard HPC practices. So this really kind of depends on what center you're using. If you're using it in an academic sense and on a, say, a professional or corporation-owned cluster, it really depends. But on kind of shared academic clusters, these are some kind of standard practices. First off, you're only going to have remote access to these. You very, very, very rarely are going to be able to plug in a keyboard, a mouse, and a monitor to a login node and be able to work from there. So usually you use Secure Shell or SSH via a laptop or workstation, a web application such as Open On Demand, Or you can even sometimes have like a Jupyter Hub or a MATLAB program that can talk to the cluster. So you are writing either Python or MATLAB code that can submit jobs and work to a compute cluster. HPC clusters are typically Linux-based. Just a lot of the software that was created to make HPC clusters was written in Linux, and then also, licensing fees and things like that make it typically the operating system of choice. You almost always have a job scheduler that will prioritize and allocate resources based on these job requests. And then you'll usually have queues or partitions that have some sort of constraint on what you can request. This can be things such as, you can only request this many resources, or you might have your nodes broken up by node type. Hey, these are my GPU nodes. You submit to the GPU partition. Or if you have multiple generations of CPUs, each generation might be its own partition, and you submit directly to that. Software is typically accessed via a module system, so a lot of centers will build software that is useful to multiple groups, and sometimes even just to specific groups if they're large enough. Because there's so much software installed, you don't want all of this in your path, in your library path, if you're a coder, if you know what that is, just because it might create weird dependency issues. And you might even need multiple versions of the same piece of software, because if you want to be able to reproduce something, or maybe you wrote some code that only works with a specific version of MATLAB. So you use this module system, which typically all it really does in the background is set different environment variables like your path, your LD library path, C path, things like that. There's usually multiple different types of nodes. There's going to be your login nodes, which is where you log in, obviously. Sometimes there's interactive nodes. There'll be some way to get an interactive job or interactive access to a compute node. So maybe you do need to compile on it or run some debugging stuff in a interactive way, and not just have to wait for results to come back in. There's usually compute nodes, where the work actually happens, and then sometimes there are going to be these data transfer nodes. So if you have multiple file systems at your center, there might be a specific set of nodes that are dedicated to transferring large amounts of data back and forth, so it doesn't impact the network on other things. And then finally, there's typically multiple file systems for different files and use cases. I touched on this a little bit in the previous slide. You usually have a file system for your code. You'll have a file system for your large files, and then you'll have something for like long-term storage, for example. So, compute nodes. Most storage on a compute node is shared storage. Local file systems are optional. Typically with the advent of kind of GPU compute nodes, you've been seeing local storage come up a little bit, because transferring data in and out of GPUs via the network can cause a little bit of slowdown. The operating system image is usually installed into memory. You don't really want a lot of moving parts, because these things can, it's another part that can die, and then also you want it to be easy to change out operating systems. And then the software is going to be installed either in the OS image or on some sort of shared storage. And then you usually access these through batch mode. You submit a job request, it goes to the job scheduler, and then you wait for the results and wait for it to run. Kind of different types of file systems that are typically available to an HPC cluster. Usually there is a network file share. These are kind of your high availability, maybe backed up file systems. Ceph, Versity, ext4, Isilon, all sorts of stuff. This is mainly used for code, software files that are needed for the jobs to run. There's also a parallel file system. These are done usually for larger files. These allow a file to be accessed by multiple processes at the same time, because each chunk of a file might be stored in different locations. Some examples of this are going to be like Lustre, BGFS, Weka, and so these are usually used for large files that you're running on the compute node. And then finally, there's the archive long-term storage, Versity, QFS. These are usually for results that need to be stored for a while, or if you're going through many large data sets, you might be able to put some, and your programs take a long time to run, you can put some into an archive to sit there and wait until you're ready to use them. And usually it's a magnetic tape-backed file system. So I want to touch a little bit more on parallel file systems because there's a little bit of a concept change compared to your normal file system on a hard drive on your phone or on your laptop or desktop. As I kind of mentioned before, these are used to access files in a parallel fashion. So this means it's generally better for large files that can be broken up. And then also if your program can make use of reading a file all at the same time. Parallel file systems generally store the metadata about a file, kind of where it is, what the name is in one location, and then the actual blocks of a file system somewhere else separately. Which means there needs to be a network connection between your kind of metadata and where the actual file is. And so you kind of think you have to hit this metadata server first before you can actually go to the file. Generally, it's accessed over the network. In HPC environments, it's generally a scratch space. And then finally, your network speed is going to be important here. If you have a slow network, then that's going to just slow down everything. And just a little bit of a diagram of what a parallel file system can sort of look like. So you have a metadata server. This stores all the information about a file, where it is, where each of the blocks are, and things like that. And then you usually have what are called object storage servers, which is where the data actually resides. So these can be separate. The shades and colors here kind of represent maybe different files. So you might have a file that is on all three of your object stores. So if you have a program that can read from each chunk of it, you can read all three sections at the same time, which can give you some speed up rather than having to wait for a file to open, have part of your process read it, then close it, then the next one can read it. But another thing that's kind of important to think about with these parallel file systems is you kind of have two actions to access a file. You have to read its metadata, hey, where is my file? Where's the next block of it? And then actually go and retrieve that block from another location. I bring this up because small files, if you have a lot of small files, it tends to actually bog down a parallel file system because if you're reading, say, 10,000 small files, you're kind of doing two operations per file read. You have to hit this metadata server, then you have to hit your storage. So it's just something to be aware of when you're working in parallel file systems, that it's better if you can keep your files as large as possible. So I've talked about this a little bit. Parallelization is how you get your speed up on these high-performance computing clusters. So why? Why do we do this? Wouldn't it be much better if we can just make a really fast CPU? Unfortunately, there's just been these diminishing returns on increasing CPU speed. It's just one of those things where physics and technology makes it really, really hard to make CPUs faster than we have, just due to all sorts of stuff, manufacturing, cooling, a lot of things like that. And then additionally, you can always add more CPUs or more nodes. Say if you did make this incredibly fast processor and then you wanted to go for an upgrade in an HPC cluster, if your code is reliant on that processor being very fast, the only way that you'll be able to speed it up is by making an even faster processor that you'll need to then replace. Whereas if your code can just split across multiple CPUs, you can just add more, and then you can get even more parallelization. So what are the different types of parallelization? Well, first there's multi-core. So this is confined to a single server. So you're not going to have any sort of network communication between this process and any other process. So it means it's confined specifically to a single node. Here you'll hear the main technologies used for this are going to be things like OpenMP and threads. So this will either be, you can spin up more processes or more threads on a single server, or you use OpenMP, which does that kind of for you in the background when you program. You can also use what's called background processes. So say you have a script that reads, that you have some input data for, you could run that script like, 20 times on 20 different sets of data and run it in the background on Linux. And that would be kind of a cheap, easy way of doing multi-core parallelization. Next, there's multi-node parallelization. So this is you have multiple nodes and you can communicate across the network to different nodes to kind of update state and things like that. So like the program can know when the job is done, or if your code is reliant on multiple parts being data being processed, and they need to wait for all of it to be done before it can move to the next step. This also uses distributed memory, so the memory on each node and each of your nodes will be separate, and each of your processes. And generally use something like MPI for this, the message passing interface. There's probably some other technologies there too, but MPI is the big one in the HPC space. And this just sets up a communicator where your nodes can all communicate with each other and kind of update position or pass data back and forth. Finally, in kind of the newest type is using GPUs or graphics processing units. So you have your graphics card that can run a bunch of applications all at once, a bunch of computations all at once on a set of data. You'll definitely hear this in the artificial intelligence machine learning field. And you usually access this through CUDA, OpenCL, and HIP as well, which is AMD's sort of competitor. So, and just to give kind of a brief overview on how you actually run stuff on an HPC, run programs and applications. First off, you use a batch job. You write a script, or again, you can invoke this from the command line usually, that says, hey, this job will need this many resources, will have this time limit, and then that's submitted to the job scheduler. And the job scheduler takes all this information, puts it in its queue, and figures out, hey, this is when I can schedule it, based on my current information, the current stuff I know of at this moment. Usually have to copy your files over, copy your code. So then it goes to the job scheduler. This is a resource request. There's multiple types of job schedulers, Torque, Slurm, Moab, tons of other ones that you use. It's a piece of software that can take in a job request. And then you have your prioritization scheme. There's stuff like first in, first out would be kind of the naive way of doing it. You can also have different prioritization schemes. It might be, hey, this group is more important because their research needs to be more real time. Say they're operational. They need to get out weather forecasting very quickly in a timely manner, so they might have a higher priority. Different prioritization schemes can even preempt jobs. So if, say, you're doing weather forecasting and you're on a shared system, maybe these weather forecasting jobs will shut down other jobs and run first. It really depends on the center. And then finally, there's usually some sort of backfill algorithm. Basically, if you set a time limit on your job request, say, hey, I know my program's going to finish up in 3 hours. Probably take less, but at least 3 hours, at most 3 hours. A lot of the job schedulers can try to fit that job in between larger requests. And then resources are tracked by a job scheduler, and then your allocation usually has some sort of reporting mechanism to it, some sort of you've used this many core hours, or you've used this much of your fair share, based on kind of the resources that are available and how much you've been using. I'll probably talk about that in a further lesson. All right, and that's basically a broad overview of HPC high-performance computing and some common terminology. Thank you.